first talk in this panel is going to be given by Aurora Bozzini from the University of Padua, and this is entitled Remote Detection of Spruce Bark Beetle Infestations in the Italian Alps. Please, Aurora, the floor is yours.
Thank you very much for inviting me today. I'm going to talk to you about remote sensing techniques applied to the study of forest pest population dynamics in the northeastern Alps. And so our study is part of the Dolomites 2 project, together with our partners from the Free University of Bozen and the Bock University of Vienna. I'm going to summarize very quickly some concepts that have already been explained this morning. So the subject of our study is Ips typographus, an Eurasian bark beetle that attacks Norway spruce and kills it at the larvae stage. And Ips typographus preferably attacks weak or recently dead trees in which the phloem is still fresh. And this characteristic is what makes this pest so harmful to forests that are already damaged by other abiotic disturbances, such as storms, snowfalls, or wind throws, like the violent viastorm that impacted on the northeastern Alps in the winter of 2018. After extreme events like this, in fact, the bark beetles dispose of a large amount of damaged trees that, if not properly managed, can become a favorable environment in which they can grow in population, eventually causing outbreaks and expanding onto healthy stands also. So as we know, extreme weather events like these are going to be much more frequent due to climate change, and it's even more important to develop effective techniques to prevent population outbreaks and limit further ecological and economic damages. So for this reason, our project aims to integrate the biological and ecological information on Ips typographus with the remote sensing information on the health status of the trees in the Alps forest to assess bark beetle infestation dynamics. In fact, through satellite imagery, we can try to detect and map bark beetle infestations at the early stages, gaining useful information to help forestry operators better manage the damaged material and prevent further expansion. To do this, we rely on the imagery from the Sentinel-2 mission of the Copernicus program of the European Space Agency, because it presents several benefits, such as a high revisit time, high spatial resolution down to 10 per 10 meters pixels, and also multispectral resolution with 13 bands in the visible and infrared spectra. All of this while being available for free on the Copernicus Open Hub. So all of these characteristics determine a high potential use of this imagery. To assess the health status, the vitality status of the trees, we use the so-called vegetation indices that are calculated using certain spectral bands from these images. So the most commonly used for this purpose is the normalized vegetation index, as known as NDVI, which, as you can see, is calculated using the near-infrared and the visible red spectral bands. Here I wanted to show you an example of an NDVI image of one of our study areas, from which we can then extract our potentially detected areas. We don't use just one vegetation index, we use a combination of vegetation indices because this method has a greater ability to detect vitality variations that can be possibly due to forest pest attacks. So here you can see an overview of the procedures we follow. We start from an important phase of pre-processing of the images, in which we work on a time series of images with a low cloud cover percentage, on which we then calculate the indices that we want to consider, and we select our study areas. We then proceed to calculate the indices variations between different years, and we set threshold values to detect variations and define variations that can be due to bark beetle attacks, from variations that can be due to other disturbances. This way we can locate our potentially attacked areas that will have to be verified in the field. Field surveys are in fact, Field surveys are in fact a really important part of the study, because not only they allow us to validate our results, but they also allow us to obtain precise GPS positions of both actually healthy forest and actually infested parts of the forest. So from this position we can extract indices values that correspond to the real health conditions of the forest, and we can create a data set of values that can help to better calibrate our parameters and improve the method. Anyway, when working with the satellite imagery, we need to consider the differences in light reflectance behavior due to different sunlight exposure conditions. In particular, we can have differences in reflectance due to different factors, such as the presence of shadows, the variation in the sun position between different seasons, and also the aspect, that is the different sunlight exposure of different versions of the mountains. For example, as you can see here, the satellite imagery can be more reliable on the south exposed versions because they are the one directly sun exposed during the day. And there are a lot more spots detected on these north exposed versions, as you can see, but these results can be caused also by noise due in fact to the reflectance differences, and this has to be taken into account. So in this context, the characteristic features of the alpine landscape pose some difficulties in the application of remote sensing techniques, starting from the availability of cloud-free images to landscape irregularity and all the differences in light reflectance that for the reasons just exposed. And all these factors have to be considered when interpreting the detection results. So to overcome these issues and improve the method, we can focus on some strategies, like finding vegetation indices combinations that are more susceptible to variation in trees due to pest attacks. We can create a solid data set of indices values that correspond to different conditions of both light and health status of the forest, and this would be really important to better understand the reflectance behavior of infested regions. And finally, also the integration of machine learning techniques can be really useful to evaluate the detection results, in particular if applied on large areas and regions. So thank you very much for your attention.
Thanks a lot, Aurora, for the view from space, from far away. This is, I think, going to be more and more relevant for all and many different disciplines. So now we are sort of focusing on the very local aspects by looking at the opportunities and limits of unmanned aerial systems, or drones in sort of normal words for environmental monitoring. And this is going to be given by Gernot Paulus from the FH in Kärnten. So please, Gernot, the floor is yours.
Yeah, thank you very much for the introduction. Also special thanks to John and Alessandro for the invitation and having me here today. And I would like to give a high-level overview about the use and applications of unmanned aerial systems, also known as drones, in the context of environmental monitoring, and also discuss with you a little bit the opportunities and also the limits of these innovative systems. So I'm Professor for Geoinformation at Carinthia University of Applied Sciences for more than 20 years now, and since 10 years I'm leading the research group SIENA, that stands for Spatial Informatics for Environmental Applications, and here we're interested to use drones for different applications. And here you can just see some impressions and examples of different systems. So we use here fixed wing systems, rotary systems, also systems lighter than air, which are actually balloons, for application areas like measuring snow height in alpine terrain, understanding flow patterns close to fish passages at rivers, precision viticulture, and also, of course, forestry. So just to put now these unmanned aerial systems in a nutshell, what are these opportunities and limitations. So at first, I think it's really a cool technology, cool in the sense that we communicate this as a sort of an entrance to attract young people and also young researchers into this field. It's also now becoming more and more mature, specifically also for environmental monitoring. And this is also providing a sort of a connecting link between measurements and observations on the ground and what we have just seen before in the presentation from space. So to look a little bit more into detail, we have here now a system which is really highly flexible, which means if we do a mission in the morning, we can actually start an automatic processing chain and have the results of this mission, of the specific plot of land, at the same day. We even can do multiple missions a day, for example, if you're interested in diurnal changes, and theoretically we can do this 365 days a year. We have meteorological constraints. We cannot fly if it is too cold, if it is too windy, if there is precipitations. On the other hand, we do not have this cloud dependence, what we have with satellite remote sensing, because we actually fly quite low, close to the ground. An operator is required, which means you need some skilled persons to be able to fly the systems safely, but on the other hand, it's also a safety issue, and this is also important. What we can get here is really not only a high resolution, but a very high resolution at comparatively low costs. Very high resolution means that we are actually able here even to create auto images, georeferenced images and 3D models, even at the single leaf level, if this is necessary. This, of course, causes also a lot of data management efforts. So we are not here at the moment like we have it with the Copernicus, that you really have a very nice access to this data in a structured way. So we have to deal here with a lot of processing issues. Another advantage is we can change the payload, which you cannot do on a satellite, of course. So we can use different types of sensors. Of course, operation of drones is related to a lot of concerns. So we have to face here restrictive legislation. So people are very concerned about privacy, for example. But the good message here is that since 2020, we have here a European-wide standardized legislation for the use of drones here. And this is make things in the future definitely easier. It's a clean system with electric propulsion. We only can do limitations in terms of the area we can cover, but this is also improving by becoming more capable systems. And there we also have a lot of application domains here. So if we would like to put this now a little bit into perspective to other remote sensing technologies, I would just like to discuss with you here today this interdisciplinary innovation network for multi-scale environmental monitoring. And this is actually meant to present here a sort of a holistic approach and also framework to the digitization and therefore also quantification and also documentation of ecosystem services. We have heard a lot already today. And this system here actually, so this framework consists out of different pillars. I would just like to discuss a little bit today here now in detail. On the one hand, we have the application domain. This is driving a lot of the use of these systems. So it really ranges here from water management, meteorology, air quality measurements, biodiversity, agriculture, viticulture, and of course forestry. So, and every application domain has its specific needs which needed to be considered. We also then have different platforms. So we have on the one hand the space segment with the Copernicus and Sentinel satellites. We have the segment of the air, but we also have these type of systems possible to operate on water and also even on the ground. And these platforms are equipped with different types of sensors. And these sensors here we have really incredible set of possibilities available here, ranging from very high resolution RGB cameras. We can actually even equip here laser scanning. We can have radar systems, we can have thermal cameras, and also multispectral cameras. And these multispectral cameras, for example, here can also operate in the same spectral range, but with a much higher resolution, for example, as the Sentinel satellites we have just seen also before. And then with the sensors and this platform, we can cover environmental data. And these environmental data here then needed to be processed, where we have also a rich set of different types of analysis approaches, and Anna also showed some examples here of mapping these ecosystem services. So it's spatial-temporal analysis we can do here based on these digital data, then 3D and 4D visualizations here. We can also fuse the different data from the different scales together and also provide here machine learning techniques for automated classification. A very important point here in this whole framework is, of course, the quality assessment, because at the end of the day, the customers will actually really need validated data in order to be sure to make here then a good management decisions. And what is of course also important here is that the overall legal framework. So we have now this European-wide legislation for the operation of these unmanned aerial systems, but also things of business development here is also important.
Gernot, excuse me the interruption, so you're running out of time.
Okay, so yeah, I'm almost finished here. So these are just some 4 customers here, ranging from the governmental sector, the application domain, from sensor data and customers, and also, of course, there's a strong need for research and development from an interdisciplinary perspective. And the last point here is actually at the end, where this environmental service solution actually should provide, are actually data and information for making better management decisions, and this is to understand and also quantify the change. So we need change detection and then also the impact assessment of these changes, and this should help also at the end of the day to reach this United Nations SDG goal number 15 and also to support here the managing sustainably of alpine forests and reverse biodiversity loss. Thank you.
Thanks a lot, Gernot, for the information and challenges for the details, for the very local exploitation. And then we are quickly moving on to sort of a big international system, so the Copernicus EMS rapid mapping service in dealing with the consequences of the Vaia storm. We have already heard about this storm in 2018, and this is going to be presented by Lucia Luizietti from eGeos in Italy. Lucia, can you hear us?
Yes, very well. Can you hear me?
We can hear you, and we can even see your first slide, so please go ahead.
Okay, good morning everybody. Thank you for giving me this opportunity. I'm responsible in eGeos of Emergency Services and Operation, and I'm the technical coordinator of the Copernicus EMS Rapid Mapping Service. Okay. The Copernicus Emergency Management Service is part of the Copernicus program implemented by the European Commission to monitor and forecast the state of environment on land, sea, and in the atmosphere in order to support climate change mitigation and adaptation strategy, the efficient management of emergency situation, and the improvement of the security of every citizen. The Copernicus EMS use satellite imagery. We already seen several examples today, and others show spatial data to provide mapping services to address natural disaster, human-made emergency situation, and humanitarian crisis throughout the world. In particular, the rapid mapping service provides geospatial information within hours from its activation in support of emergency management activities immediately following a disaster. Since 2012, IGEOS is the group leader of the consortium that is providing the Copernicus MS rapid mapping service with continuity since the operational phase. This picture in this slide shows the distribution of the rapid mapping activation. We collected 547 since 2012 per event type. You can understand now that the service is monitoring the evolution of the lava flow in La Palma, and we are still receiving requests for wildfire events. During this summer, we supported more than 30 rapid mapping activation inside Europe. It was an exceptional wildfire season. In October 2019, the rapid mapping service was triggered by the Italian Civil Protection for mapping the damage made by the Vaia storm. Indeed, as already showed in previous presentation, extreme meteorological events are important causes of damage even in the alpine environment, characterized by strong winds that can damage infrastructure and alter intensively vegetation. The Italian Civil Protection triggered the service a few days after the event for a fast analysis based on satellite imagery. This quantitative analysis was relevant for understanding the magnitude of the event and for identifying the most affected area where the attention of decision makers need to be focused on immediately after the event. It cannot be considered for sure an exhaustive analysis, but in few days a huge area was analyzed in order to identify and delineate the area with the loss of tree cover. Over 4 regions, 4,200 hectares of loss of tree cover were detected. This picture shows very well the situation after the Vaia storm, acquired by very high resolution optical data. The analysis were based on a visual change detection and not a machine learning approach, because we have a few hours for deliver the product with a high accuracy of the content of the product. And so the analysis were based on a visual change detection between a pre-event and a post-event imagery. In this way, it's possible to perform an accurate delineation of the affected area. This kind of rapid mapping product is delivered within 9 hours, so it's a very fast product since the availability of the post-event satellite images, and the user can use data for further analysis in their system. This is a very important point for the user analysis that can be finalized after the delivery of the rapid mapping products. This is another view of the satellite images used for the analysis, and this is another interesting view of one of the affected area 1 year after the Vaia storm from the Copernicus Open Sentinel-2 imagery. The affected area are clearly visible and can be, for sure, as already remarked by the previous presenter, can be monitored using Copernicus Earth observation data due to the good resolution, due to the high revisit. And so it is a powerful tool to monitoring the evolution of the situation after the disaster. After the analysis performed in Italy, the rapid mapping service was requested for the same event also in Austria. So in this picture, there is a similar production over additional area of interest defined with the Austrian Civil Protection. At the end, in this case, we defined 17 area of interest, and again, we based the rapid mapping product on the analysis of very high resolution optical imagery. All the areas were defined on the border with Italy due to the fact that at the end we monitoring the same event with a different effect in Austria. This is my last slide. I know that we don't have a lot of time, so thank you very much for your attention.
Thanks a lot, Lucia, and especially also for perfectly being in time. That's great. And with this, we are moving, so to say, from the way how we get the data, so how we observe all this information, to what we do with it. And that's this last presentation in this second session. And this is entitled How Artificial Intelligence and Big Data Platforms Can Deliver New End-User Services for Forest Management. It's going to be presented by Laurent Clerge from Atos in France. Laurent, can you...
yes, I can hear you. Good morning, everyone.
And we hear you, and we see your slide, so please go ahead. The floor is yours.
Yes, thanks to you. I'm really happy to present you our positioning after all the presentation this morning. I'm responsible for Atos of the development of sustainable services, focusing for sure on decarbonization and climate change impact. Then in this way, we present some technical elements and how we address end user services for forest management. As already said this morning, the forest environment is really complex, and to address it, we build complete ecosystems of technology and also research centers and experimental territories for demonstrate how we can solve issues and problematics for end users. Then a first element, and some of my colleagues have already explained what is it. We operate an industrial platform for the European Space Agency in Europe to give a easy and efficient access to Copernicus program. And we have built a biggest platform on that with a specific consortium. And based on that, with a big volume of data for sure, more 30 petabytes of open data, one image each week, and more of 5 years of archives, we have a positioning to create new services for end users. In link with what we have already heard this morning, we have a lot of scientific research and results, very interesting to promote and to extrapolate, but the problem is really how to reach the end users. And that's really our positioning with this platform of Earth observation, but also with a specific and historical activity of Atos to create industrial platform dedicated to ingestion of different kind of data, compute it, and disseminate end user services. And we are actually building a platform dedicated to territories and connected territories, who is able to integrate multi-data sources from Earth observation, but also Internet of Things, and integrate all of industrial parts as service level agreement, but also creation of catalogs of scientific algorithms validated by partners in terms of research laboratories, but also middleware components and a lot of things necessary to disseminate science, big technology component and big data to end user with a high qualified level of information and a sustainable way also to ensure a complete service during the time. Here, a quick view of our organization. On the left part, we have technical element, technical components, Copernicus for sure, and Earth observation. We have also elements on drones and IoT, all ground data sources we have in front of us and often in the property of our customers, and globally the open data. To validate what we provide to our customers, we create partnerships with R&D and laboratory centers in different ways, thesis, postdoc, or a specific integrated team with these laboratories to use all the resources we are able to provide in terms of Earth observation, but also in terms of all data ingestion to create a big family. His name for the moment is Green Care, who is able to provide tools to measure territory efficiency, to address different levels of actors, big actors in terms of institution, public or private, but also local authorities in terms of management, but also policy roadmap and policy makers, and some of components linked to all of this complex system with application for citizens. That's the overview. For today, we address some of parts of forestry on sustainable development services in terms of food security, but also biodiversity preservation, air quality, carbon sinks, and a lot of things we have already heard. Then I will save time on this part. You know it, and some of experts have already explained. Specifically for large-scale forest monitoring, we are able, with all elements already explained, to create maps for sure, but the interest is also to create already available services for our customers to inherit of the archives of the imagery from Copernicus, for example, to ingest in the artificial intelligence knowledge specific to understand what is expected in the past and how to prevent the future. And on this way, on different thematics, and you know it, and some of other aspects I've already explained. From my part, I will focus on specific existing services to show that's not a dream, but a reality now. For example, here on the north of Milan, I have opened a dedicated service created for the COP26 and operate by the platform and for the future. And we have compute automatically a filter already explained by a colleague just before on NDVI mapping to integrate automatically, and that's available at global scale for all the Earth, and each week automatically to help and to support users to directly use this add value data in algorithm and create direct thematic add value. That's, for example, for Milan, and we base that on Sentinel optical and also Sentinel-1 SAR radar. Based on that, we can go over to focus on. Sorry, I will just jump in another, but I have the bad. Yeah. Thanks. Here, an example of the combination with different add value data to help cities and to replant, in fact, inside cities, but that's the same problematics in mountains. For example, here we have combined hotspot detection, vegetation monitoring to provide directly indicators to prioritize actions. Then on this little example, the interest is to see in some seconds how with a big platform on the cloud and artificial intelligence, we are able to compute big volume of data to provide intermediate add value data to thematize what is the content of imagery and verticalize it regarding the job of the needs of the customers to provide really basic indicators to prioritize the actions and so on. And this process is only available because with our partnership we're building before with our partners and laboratories to ensure high quality of this decision help data. And that was the exercise I will happy to present you today. Then I don't know if that's sufficient, but the interest is really to see all elements already heard and discussed this morning can be not easily, but that's possible to create industrial end user services to help decision makers to bring a new decision based on data and qualified data validated by science and laboratories.
Okay, thanks a lot.